Okay, for today, let's just jump in with the examples that we left off with last time. I'll do some announcements in a little bit, but it looks like we're a little on the low side people-wise, so better to let everybody come in. So you guys all kind of tried to do this at home without me first, right? Yeah, if not, no big deal. You just are going to try to beat me to each step. So we haven't done problems like this, technically, kinda, but you know that this really isn't any different at its core than what all the stuff we did last chapter was. And so because of that, you should be able to at least get kind of the setup. You may not be able to beat me because of calculations and things like that, but try to beat me to all the setups of the steps and at least knowing which number I'm going to fill in. Okay? All right. So we have a pH of a 0.3 molar solution of a weak base is 10.66. What's the Kb of the base? Now, this is a case where we do have a little extra add-on step compared to what we had last chapter. Also, I'm kind of getting sick, so it shouldn't be too bad, but if I start getting quiet on you as the class progresses, feel free to like throw a hand up and tell me to get louder again, just because it might happen as the class goes on. Okay, so our first step, we do have to write the equation. Before I've always given you the equation, or the book has always given you the equation, now we have to write it. It's not too bad though, because we have a weak base. So we pick a generic way of writing a weak base. I generally do it one of two ways. I either do A minus, sometimes I'll write it almost as if I'm writing the conjugate base, or I'll just start with B. Either way is fine. And then for a base, you pretty much always have to have water there because you need something to pull that hydrogen from. With the acids, we can just split it up and kind of pretend that H plus is allowed to exist on its own. With the base, we usually have to put the water there. It's weak, so it gets equilibrium arrows. And then it's a base, so it's going to steal a hydrogen, which makes it a plus. And it's going to leave off an OH minus. I don't tell you a lot here, so we do have to pay attention to what we do know. We're probably going to want to make an ice chart. Don't have to, but probably. I have a 0.3 molar solution. When I give you the concentration like that, what is that always referring to? Initial or equilibrium? Good. Initial. As usual, I'm going to kind of drop sig figs so that everything fits nicely into the chart. Whenever we start these, what is our initial concentrations of these? 0, right? I haven't had a chance to equilibrate yet. They're 0. Okay? Now, at this point, if you go on autopilot, which often happens, especially after last chapter, and you fill in minus x plus x plus x, and you fill that in down here, and you go to fill into Kb, what do you find out that we don't have? Kb, that's what we're trying to figure out, right? So if that happens, it's not a big deal. It does time to time. Let's go back and see what we haven't used yet. What haven't we used? We haven't used the pH. But if we use the pH directly, what concentration does that tell us? H plus. Do we have H plus in this equation? No. What do we have though? And so what can we use to find the OH concentration? 10 to the negative POH. Now make sure you know where that 10 to the negative is coming from, right? That comes from POH equals what? Negative log of OH minus. But how do you undo a logarithm? 10 to the power of. So this isn't like a new equation or something like that. It's just the algebra rearrangement of POH equals negative log of OH. Okay? Don't forget the negative, or you'll get a weird answer that doesn't make any sense. So make sure you remember to do the negative there. And that just accounts for that negative log of. And from here we get our OH minus. So a little different than before because we have to do this extra step, but this whole middle part's the same. Because now we just take this, we fill it into here. And now we're probably back to the point where you might be able to beat me as you go along. So now we have that initial and final value of the same thing, which means that we know are what we could call plus x, right? If we call this minus x plus x plus x, now we know that. I'm going to switch to purple to indicate, hey, this is stuff that we've now figured out. If you hate the color purple, don't worry, you can use whatever color you want on your notes, it won't make a difference. And we fill all that down. Now we fill into our Kb equation just like we used to fill into Kc or Kp. In fact, this part is usually a little bit less mistake prone than for Kc or Kp, just because you don't have to worry about the coefficients. They're almost always 1. Not always, but almost. And obviously you're welcome to write that as squared. I wrote it separately, only for the sake of not getting you confused with it. It has nothing to do with coefficients or anything like that. It's just each of these. So write it however you want. Should I put a unit on it? No, it's a K. Brief discussion on this. So the T's that were grading all the math problems on your exams did tell me that there was some pretty significant not putting units on things. Kc doesn't have units, and so we don't put units. Kp doesn't have units. Ka, Kb, none of those things have units. But all those other quantities that we have in chemistry, they still have units. So be really careful to make sure that you're not getting in a habit of not writing units and then carrying that over on other problems. When you get done with these problems, you should think to yourself, I am not going to put a unit on that because that doesn't have a unit. Don't get lazy and just start being like not putting units on things. You see the difference? One is like an active decision. I am not putting a unit on this, as opposed to just leaving it off, which becomes a really bad habit that you'll carry on to other things. Units are super, super important. I don't grade particularly difficult on sig figs because as you progress in life, those are they're going to matter at times, and you're going to know when they matter. Units always matter. So be really careful with that. Okay, one other question for you on this one. Last time, we learned about the fact that we can do some things to make our calculation simpler. And that's that on these problems where we have a pretty big concentration initially, and we have a pretty low Kb or Ka or Kc or K whatever, that we're allowed to ignore this. Yet, here I put it in. Should I have decided to leave it out there? Should I have made the assumption? Let's ask this differently. Could I have? Probably. So why didn't I? Does it save me any work? If I make the assumption, what do I have to do? I have to check it, so that's a little bit of work. And I'm not being there's an automatic lack of accurateness when you do that. It's enough that we don't really care most of the time, but you are losing some accuracy. And was this a difficult thing to type into your calculator? No, so don't do it. The assumptions are meant to save us time and energy, and especially when it doesn't matter. Something like this, we have the number. We have this number here because of this and this and this. It doesn't save us much work. It's not really worth it. Don't make an assumption if you don't have to, or if it doesn't save you a large amount of work. So that's why I didn't do it here, and why I would suggest not doing it, even though technically it would probably end up being okay. Okay, questions? Next one. Definitely try to beat me to this one. This one is very similar to the last one, except that I just ask a slightly different question. Instead I say, what percent is present as that? It's really pretty much the same thing though. We'll start out by writing our equation. I could write out this whole thing, but it's a lot faster if I just write this. And so that's what I'm going to do. With the weak acid and base problems, you can always write it as just a generic equation if we don't specify otherwise, and it saves you some time. We make our ice chart. Where does this go in? Initial equilibrium? Initial. And what thing down here does it go under? What is this? Is it an acid or a base? It's a base, because it's that nitrogen with 3 bonds, right? When you see that nitrogen there with some hydrocarbons on it, think base. And if you didn't know that, I give you another hint over here by showing you that it picks up a hydrogen. So there's some hints there. So we'll fill that in. Initially 0 and 0, just like before. And now what we're trying to solve for is this. That's what we want. I tell you the KB. Whenever you're given the KB, you can actually then kind of look and say, well, I can probably put a variable in there that I don't know and be okay. So that's what we're going to do. We're going to fill in minus x plus x plus x. That. And now we can fill into KB just like we used to when we did KC and KP. All right. Now, here's where we want to look at this and say, maybe we can save ourselves some work. Maybe you just want to always solve the quadratic, that's fine. I'm sure that option just skyrocketed in a lot of people's opinions because of the whole, calculator thing. But let's look at the assumption anyways, because learning when you can and can't make assumptions is actually a really useful scientific skill. Because when you're spending 40 hours in a lab all day long and you think, I wonder if this really matters that much, you want to be able to have the mindset to think, does this really matter that much? That goes for medicine too, where there's all these calculations for exactly how much medicine you need to give a person, but a lot of times it doesn't matter that much whether the person weighs 120 pounds or whether the person weighs 123 pounds. And you need to have in your head, why do we make those assumptions? When are we allowed to do it? And so it's a good thing to kind of talk through anyways. So in this case, I'm going to go ahead and make it. And the reason why I'm going to look at it is I'm going to look at this and I'm going to say, okay, that is pretty low. Maybe I need to think about that a little bit. But this is really, really low, right? To make this assumption, we want high concentrations and we want low Ks. We want them to be about 1,000 difference or more. And this is, in fact, about way more than 1,000 times bigger than that. So we'll probably be okay. That's our initial kind of mental check. Is our concentration about 1,000 times larger than our K? If it's right on the borderline, it's a little iffy on whether it'll work or not. You'll have to check it. Okay? So if we want to make the assumption, we say that that x on the bottom is probably pretty small in comparison to 0.08. That it doesn't really matter that much. That answer is still going to be about 0.08. And we do that, which makes our math really easy. Because now we just multiply over and square root. We're back to using x, so I'm going to go ahead and make sure you put the unit on that so that we remember that that's molarity. Now we look at this and we have to check the assumption. We have to make sure that it works. We have to make sure it's okay. Purple isn't showing up as that different of a color, so I'm going to use this. Much brighter. Okay, so we'll do the assumption check. I would suggest not shortening that word too often when you go to write this. Yeah, it was a rookie mistake my first time teaching. We were going to put x over 0.08. Now, why 0.08? Remember, we're thinking of it two ways. We can either think of it as we're making sure that our percent ionization is less than 5%, or we can think of it very, very, very mathematically, where we don't really even bring any chemistry into it. And we say, well, hey look, X compared to that is going to be small, whichever way you want to think about it. We get that. Is that less than 5%? Yeah. So we're good. Now, actually, we had to do this because we had to check for the assumption, but if you look, what am I actually wanting to solve for anyways? What percent is present as C5H5NH? So it turns out that this is also our answer, right? Because it's also our percent ionization. So that word's a little small and a little cut off, so it just says also percent ionization, which is the thing we're actually solving for. So that took care of both things at once. You had to do it to make sure the assumption was okay, otherwise you had to go back and solve the quadratic, but it also happened to be our answer. We're not quite done yet though. What else did I ask for? pH. So what are we going to use to solve for pH? Use that, right? There's two different ways. You can solve for POH and then subtract it from 14, or you can fill it into the combined equation, which is that pH is equal to 14 plus the log of OH. To be 100% honest, when I write it, I almost always write it like that. And when I think about it, I almost always think about it as doing the negative log of OH minus and then subtracting it off. However you want to do it is fine. There's actually one other way you could do it too, right? What can you find, what do you know about how OH and H plus are related? Yeah?
For these problems, we can use our graphing calculator. Is it okay to set it up and then directly plug it in the calculator? So you want us to show that we know how to use the quadratic?
Oh no, you can use the calculator. Okay. Yeah, you never have to write out a full-blown quadratic for me. In fact, I would much prefer that you don't. Because even if you're using your calculator the old school way, where you actually type in normal numbers and calculate square roots and things like that, it's still just typing it into a calculator. I don't need to see that. Okay. I'm going to go ahead and just write log of x here, since we know that log of that is this. If you want to write in the whole number, go for it. And we get 9.04. We need to check and make sure that it makes sense. It's a base. What should our pH be? Greater than 7, and it is. It's not super concentrated. I mean, there's a decent amount of it, but it's not super concentrated. We probably wouldn't be expecting a super high pH, and it's not. So there's a logic to all of this. It makes sense. And that's always good. Okay, just a second to let you guys write it down because there's still people writing. Also, if we ever do go too fast on these and you just miss it, if I get a couple people telling me it's too fast, I'll post it. If I get one person telling me it's too fast, I just hand it to you and you can look at it and copy it down. So feel free to ask. Okay. So quick review on this section, especially because it's been a little while since we started it. So for this, we want to talk about a couple different things, right? We have our percent ionization, and I want to remind you about percent ionization just because it actually is relatively important to solving these problems, because a lot of times you're going to use it to make your life easier. So if you're, like something is wrong here. No, we're okay. All right, so a reminder on that. If you have a really high Ka, you also have a really high percent ionization. The two are related. They're not directly related. It's not like an exact proportionality for every single thing. Depends. But as one goes up, the other goes up. So you can use that to tell if your assumption is going to work or not. If your Ka is really, really high, it's probably not going to work. If it's really, really low, probably will. By that same idea, if your concentration is pretty high, you have a better chance of it working. You can use the approximation to make your weak acid and base calculations easier. And overall, I did not go into the actual problem solving here, because when it comes down to it, the problem solving is exactly like you saw last chapter. And I can't really do it all in exact detail because they're all a little bit different, right? So your main idea is you make your ice chart, you write your equation, well, write your equation first. Write your equation, then make your ice chart. And at that point, you fill in what you know. And then maybe you're all set. Maybe at that point you can solve for all the things you care about. If not, just go back up to your problem and say, what didn't I use? A lot of times the things that you didn't use are going to be your pH or POH in this section, and that's going to remind you, oh yeah, I can use that, I can fill that into the ice chart. And that usually takes care of most of your problem solving issues and how you go about it. Okay, we have filled in everybody a little bit more. So let's do quick announcements. So all this got emailed out, but just in case, I know it was a little late this week, sorry about that. So tomorrow you have your extra credit assignment. There was a little mix up with this, so I fixed it. I accidentally flip-flopped part 1 and part 2. So sorry about that. On the plus side, it just means it's going to be extended out. So I left the one that's due tomorrow where it's due. I didn't like flip-flop them on you because by the time I realized it was too late. So part 1 is due tomorrow. Part 2 is now due next Sunday, or this Sunday coming up, okay? Sorry about that. A reminder on the extra credit assignments, because I have gotten a few different people saying, but wait, we haven't done this in class yet. That's the point. So don't treat these exactly the same as you would treat normal homework problems, right? Normal homework problems you treat as, okay, I kind of already know how to do this. I'm going to try this on my own first, based on what I know, and then when I get stuck, I'm going to go look for help. That's not how you want to treat these extra credit assignments. These are for you to review, to look at the material before you come to class. They've done just tons and tons and tons and tons of studies showing that that's really important. That seeing the material before you hear it from me is really, really, really important. So that's my way of getting that to you and giving you some credit for doing it in a way that you can see. Because we're all human beings. We know just because that someone tells us that something is good for us, we don't always do it. If that was true, I would eat a lot more vegetables. So this way you get tangible points for it. You don't have to do it. You can blow it off, it's fine. It's a really good thing for you to do, and this is my way of giving you a little bit of extra bonus points for it. So keep that in mind when you're doing it. You shouldn't know how to do it. Go to your book. They're all in these are all like reading questions throughout the book. Go to the section in the book where the question is about and read it. And then look at the question and try to do it directly from the book. You may not understand what you're doing. That's cool. Put little question marks across everything that you don't understand, or big circles if that's the case. And then when I hit it in class, you'll be like, oh, okay, that's why we did that. That's why I did that. That's what's happening, okay? That's the point of those questions. It's not really a normal homework assignment. You're not expected to have any real idea of what you're doing until you sit down to look at the problem. And if you say, I don't believe in this philosophy and I don't believe in those studies, okay, blow it off, it's fine. Up to you. All right. We should finish up with chapter 17 today, I think. I don't think it should be a big deal to finish up. So go ahead and start it on both sections of chapter 17. The first one is due on Thursday. The second one is due on Tuesday. Yeah? Can you say that a lot louder? No one heard that. Okay, moving on. Don't forget, in case you weren't here last time, that's a secret till the end of class. If you weren't here last time, you guys all did really good on the exam, and I wanted to reward you a bit for taking me seriously when I said that knowing that first chapter is the most important thing in this entire class because everything builds on it. And since that's where most of the sort of you need to know that you know it sort of thing came in. I said for midterm 2 in the final, you can have a 3x5 note card, front and back is fine. Bit of a word of advice from someone who's made the mistake before. Don't make these note cards typed with so small a font that you can't find anything. Yeah, there's a temptation to do it. I've done it before. It's actually a little bit damaging to you because you waste a lot of time on it on the exam. So try not to do that. Yes, you can type it if you want though. And because of that, because I let you use it, you can use a graphing calculator too, because the scare of cheating is less than. Chapter 18 PowerPoint 1 is up. So I only put the first part of it. I'm still working on the second part of it. And so that'll be up shortly. But in the meantime, you really need the first section. We may even get to it today. We'll see. So that's up if you need it. The lecture worksheets will be up today. And the second part of the PowerPoint will be up either today or at least later this week. And I did get the email about your exams this morning, so assuming that my office hours people will spare me 5 minutes to release them, I'll release them right after class. So you'll have the actual scanned copy. Remember, regrades are done in person. I think the regrade sheet isn't up, so I will post that. Just bring me the sheet. We go over it together. We make sure that you either do or do not get the points and that you understand why you don't if they aren't legitimate. Office hours is best. If you can't make any of my office hours, I'm happy to do it right after class here. I just really prefer to do it in office hours. All right. And then last thing. So let's kind of talk about where we've gone, or where we were, and where we're going. So we've kind of hit all of the main equilibrium general stuff. We've now done one specific case of it, which is acids and bases. What we're going to do next is I'm going to actually show you why the acids and bases are a little bit different. So far, we've been able to treat them identically. And there are a couple of differences, mainly because there's a hidden thing going on in all of these acid and base problems. So we need to talk about that. After that, we'll talk about a kind of tweak on the acid or base thing, and that's dealing with the conjugate acids or bases. So now looking at what happens if instead of doing something like acetic acid, right, that's a carboxylic acid, what happens if we put its salt in? It's almost the same thing, it's not that different, but it's just a little bit of a tweak. At that point, we go into kind of a very specific part of dealing with this called titrations. Have you guys done titrations in lab yet? Okay, so you have an idea of what's going on there. We'll talk about all of that in some nice detail. So that'll be useful for you for understanding what happened in your labs too. And then at that point, we talk about one more case, which is called KSP, which is talking about, we lied to you a lot in high school. Yeah, you knew it, right? In this case, we lie to you and say that things are either soluble or insoluble when that's not the case. And we're going to talk about the specifics of why that isn't sometimes the case. There's an in-between, and that it's an equilibrium. People like KSP. I think you'll like that section. It's actually easier than pretty much most of the stuff we've done, but based on the same idea. And then at that point, we get to really switch gears. So I have been asked quite a bit, because there's no homework posted past chapter 18. I just haven't gotten there yet. What are we doing after that? We do electrochemistry and we do nuclear chemistry. Those will be almost two separate storylines. So this was kind of a collective storyline up until now and up through KSP. We switch gears with electrochemistry. Electrochemistry is kind of fun. A lot of people really, really like it. Some people just, it's not particularly hard, so generally people don't hate it. Nuclear chemistry is fun. I think I'd call it my favorite, but I think I've called a lot of things my favorite at this point. So nuclear chemistry is a lot of kind of application based. It tends to be a little bit more like, let's talk about the world. The problem solving is pretty simple, which is nice. And we get to kind of learn a lot about how the things we hear about in daily life actually works, why nuclear power is good, why it's bad, why nuclear bombs are just bad, and things of that sort. So if you were worried about where we are going, that should help you out there. We will do a few more chapters after chapter 18. Okay, back to actually doing chemistry. KW. This section is going to kind of help us see why Ka and Kb are not exactly the same thing as Kc, even though we've been able to treat it like that all the way along. And this comes into play when we need to look at what happens if we reverse the reaction. Think back to when we did Kc. If we reversed the reaction for Kc, what did we do to the equilibrium constant? This is reciprocal, right? 1 over. I heard a few people say something about a negative. What were you thinking? That's Hess's law, right? Hess's law in delta H, if you flip an equation, you make negative. Kc is different. It's the reciprocal. You can't quite do that with Ka and Kb. And the reason for that is you have this other reaction going on at the same time, and that's water. So for this, when we want to define Kw, we've kind of hit on this a little bit already. We didn't call it Kw, but we did kind of see it. What this is going to let us do is relate Ka and Kb together. So we talked about acids, and we talked about the fact that they have a conjugate base. What we would like to find sometimes is the Kb of the conjugate base. You won't find the Kb of an acid, because that's an acid, it's not a base. But you'll find the Kb of its conjugate. And that isn't just the reciprocal. We have to account for something else in there. Okay, so first of all, what is Kw? Kw comes from the fact that water is actually both acid and base. Or if you want to talk about it a different way, it auto-dissociates. So there's two different things going on. Let's first talk about amphoteric. The phrase amphoteric means that it can be both an acid or a base. Other things can do this too. Especially when we get into the polyprotic acids, we'll see this. Now, you can also just think of it as auto-ionizing. So take that word, auto, at the same time, or auto, automatically, things of that sort. Ionize, it's ionizing. It's splitting into H plus and OH minus. Let's clarify one quick thing here, just because we, as chemists, get to be lazy about something, but we should always know when we're being lazy. The H plus there, is that really just an H plus? What really happens? It's actually an H3O plus. So we're allowed to write it like that, as long as we know that that's actually an H3O plus. So we know that, so we can write it like that, and it's fine. So we have our acid giving up a proton. We have our base accepting. Now, we give this a special name. Or we give the equilibrium constant for this a special name. And we call this one actually Kw. Now, notice it's not any different, right? We give it a special name, but it's really not any different. It's just products over reactants. Why aren't my reactants in there? They're liquid. We don't count them in, right? So because of that, it's just H plus and OH minus. And we've seen this before. I think I started this entire chapter out with H plus times OH minus equals 1 times 10 to the negative 14th. I always caveated it with the, at 25 degrees Celsius. But that's where we got our H plus, that's where we got the fact that neutral water at 25 degrees is pH 7. We came up with it kind of in a circular logic with this. Now, the reason I bring this into play is I want to show you what happens if we want to find the Ka of a conjugate acid or the Kb of a conjugate base. So let's take this reaction. This is a generic acid reaction, right? This is how I've been writing all my generic acid reactions. HA goes to H plus and A minus. Pop these up real quick. So that's just from the previous slide. You probably don't need to rewrite that if you're writing everything from scratch, because it's right above you in the notes. So here we have K, just super generic, right? Keeping everything really plain and boring so that it's useful for everything. Here I have the conjugate base. I just took A minus. Remember I said we can write our generic base equations two ways. We can either write it as B, like I did on the example problems that we did up here, or we can write it as A minus. Well, in this case, I'm sticking with the A minus because I want to show, well, this is what the Kb equation of this base right here, that conjugate base is. And so I write it like this. But if we add these up, so we're doing here what we did back last chapter, where we took and we had all of the different K equations and we added them up to equal a new equation and then we multiplied their Ks. That's what we're doing here. I just picked a very specific example to show you something. So we have our generic acid, we have our generic base. When you add two equations together, what do you do to their K's again? Multiply them. Okay, so let's add these two equations up and see what happens. They're not exactly reciprocals of each other, right? So we cancel this, we cancel this, we cancel this, we cancel that. We bring our water down, we bring our H down, and we bring our OH minus down. And this is not nothing, right? This is an equation. So we have here then this relation that Ka times Kb is equal to Kw. Why did I do that? To show you that last relation and where it comes from. What that does is it shows us that Ka of an acid and Kb of its conjugate base are not just reciprocals of each other, because there's water in there too, and we have to account for that water. And this is how we do it. We say, okay, well, now we know that Ka times Kb is equal to Kw. That's the important part of this slide, okay? This right here is what deserves the big circle and the extra stars, and that's the important part. That's the part that you're going to use all the time. Sure, you should be able to explain the rest of this, but that's the part that you actually use. Okay, so how do we use it? And remember this, I want to kind of clarify, I know I've said it before and I'll say it again. Remember, this is the Ka of the acid, the Kb of the conjugate base. Or Kb of the base and Ka of the conjugate acid, okay? You can't have the Kb of an acid. You can't have the Ka of a base. So make sure you remember that as we go along too. Now we have this that we can use. And this is just one equation, right? I just rearranged it. So you may or may not want to write it. But all this is that equation that we got on the last slide. Ka times Kb equals Kw, rearranged two different ways. I'm pretty sure that I just give you the 1 on the equation sheet. This falls into the category of things that you need to know that you know. That needs to be kind of at the forefront of your mind when you're doing problems and you say, shoot, all I have is Ka, but I need Kb. You need to know that you can do this, okay? You need to know that, oh, okay, I have the Ka of acetic acid, I can find the Kb of its conjugate base. Oh, I have the Kb of ammonia, I can find the Ka of its conjugate acid. Because if you try to look up these values in the back of a table, you're not going to find it. If you try to look it up on Yahoo Answers, you're definitely going to find it, but you're not going to have Yahoo Answers on the exam. So please make sure you know that. Okay, one other thing then that comes out of this. Notice that the two are, as one goes up, the other goes down, right? They're inversely related. That makes sense. So if you have an acid, and it's pretty strong, it wants to break up, right? That's what strong acids mean. It wants to break up into its H plus, and it's A minus. The conjugate base is weak. A strong acid has a weak conjugate base, and vice versa. And that makes sense. If an acid wants to lose its proton, it wants to get rid of it, that conjugate base isn't going to want to pick up that proton, almost by definition. And this shows you just the mathematical way of looking at that too. Okay, so let's try one. I'll let you guys do this one. Give it a shot. Oh, there, that's the actual question. He looks kind of angry up there. He looks happier on a small screen. Sorry about that. Pretend it's a happy ant, not an angry one. Okay, how are we doing? We got it? Need a couple more seconds? We're okay? All right. So, real quick, on the count of 3, A, B, C, D. Or all at once, that's cool. One more time, because I actually wasn't listening to you guys, sorry. 1, 2, 3. All right, let's talk about this one a little bit. So first off, how are they actually related, right? This is one of those those questions that, again, maybe you got this one, maybe you didn't because we just talked about it, but we need to make sure that forever and always you know how they are related and that you know that you can always find one if you have the other, right? So we have our KW. So we have our A and our B equals KW. Oh, in case you forgot, the reason there's an ant here is formic acid is found, like they derived it originally from ants, so that's where the formy comes in. Okay, so when we go to do this then, when we want to find the Kb of the conjugate base, remember we're not finding the Kb of formic acid, we're finding the Kb of HCOO minus, right? We're finding the Kb of HCOO minus. We're not finding the Kb of formic acid, that doesn't have a Kb. So we do our Kw over Ka. We do have to know what Kw is equal to, right? That's a really useful number to have. It's always at 25 degrees Celsius, but we do want to know what that is. So that's our 1 times 10 to the negative 14th. And so when we go overall, we get this. I heard a lot of D's in there, if I'm not mistaken. And I think that came from just doing the reciprocal, if I'm not mistaken. So not a big deal, but keep this one in mind, that we want to do this. Okay, so review of this section. I think this particular review is important in highlighting the parts that really matter because it is kind of a little bit of a tangent we go on to describe exactly why Ka and Kb are related like they are. It's useful to know, and you should know it, and you should be able to explain it. But step number 1 is make sure that you know that, and make sure that you can relate between the two very easily, and that you know that you have that available whenever you need it. Okay? And then make sure you also know as your Ka increases, your Kb of your conjugate base decreases. So they're always inverse, right? As Ka goes up, Kb goes down, and vice versa. So in terms of weak versus strong, what that means, because that's an important thing too, you may actually want to write it right underneath it, is that the stronger your acid is, the weaker the conjugate base is. So let's say that exactly like that one more time. The stronger the acid is, the weaker the Kb is, or the weaker the conjugate base is. And then the reverse of that, where if you have a strong base, its conjugate acid will be weaker. Okay? Yeah?
For the second bullet, it's conjugate acid for the acid being.
Yes, thank you. Fix that real fast. So you guys see what she's saying? Thank you. All right, so if you guys have your slides printed out, just make sure you fix that too, because that'll be on your slides as well, that little copy paste mix up. Okay. Now the reason I emphasize those last 2 points is that that actually leads us into what we're doing now, right? So the stronger the acid, the weaker the base. Conjugate. The stronger the base, the weaker the conjugate acid, and vice versa. Now, this section should not really be anything new exactly. We're just building, once again, kind of just keep on adding steps. What we're going to do now, though, is shift how we think about these a little bit. We've been giving you all these acids and all these bases, and we've been saying, okay, acetic acid is an acid. And then we have its conjugate base, which is acetate. Or ammonia, NH3 is a base. And we have its conjugate acid, NH4+. But we're almost saying right in there that that conjugate acid or base is an acid or a base, right? That's kind of built into that sentence. And that's what we're going to actually say explicitly here. We're going to say, okay, now we actually are calling these acids or bases, where before we were only really talking about them in relation to something else. So we're going to want to look at salts now and say, is this salt acidic or basic? Because some of them are. If we have something like NH4+, we can't just have NH4+ on its own, right? We can't have plus ions on their own. We can't have something like, I'll just keep using acetate, like an acetate ion on its own. It's an ion. We have to put it with something else. So we put it with like a sodium or a potassium, something like that. Well, now we want to be able to look at those salts and say, are they acidic or basic? Using this idea that we almost kind of have developed when we started talking about conjugate acids or bases. And then we'll use what we just did to figure out the K or Kb of the conjugate. So, I know, these are good. This one's actually really important so that you don't wind up in jail. And since we're talking about salts, it seemed good to put it here. So please do not throw sodium chloride at people in the lab because that's a salt. I got real laughs on that one. I'll give you a minute to explain it to your neighbor. If your neighbor isn't laughing, explain it to them. If they're still not laughing, no, that's their fault. Okay. We're going to start this section with something that I'm going to call a stepping stone example. And what I mean by that is this first set of problems are not things that I would ask you, okay? The reason why I'm doing it here is because it's a piece of all the real problems. And if you don't have this little piece, then you won't be able to do the later problems. But if I just start off with the hard problems, sometimes people get a little bit lost. And so I'm calling it stepping stone examples. So we're going to start with the ions. I'm not going to start with a full-blown salt. And that's just so that you get the hang of what we're doing. This is actually like the last step of the problems. And then we'll work back to where we're doing whole problems. Okay, is an NH4 ion acidic, basic, or neutral? Now, we can think of this a couple of different ways, as with everything. What is this kind of like that we've talked about? What's the conjugate base of this? NH3, right? So what would you call this if I instead said we have NH3 and NH4 plus? You would call NH3 a base, and you would call this its conjugate acid. So just on that, would you expect this to be acidic, basic, or neutral? Acidic, okay? If you like thinking about it that way, definitely think about them that way, because that's the quick way to go about them. To say, oh, okay, I recognize this as a conjugate acid. It's acidic. I recognize this as a conjugate base. It's basic. But we should still be able to also write the equations too. So I'm going to do that. But we already kind of have the answer, right? So I'm going to go ahead and write the equation so that you have it, so that you can see what's happening. We have NH4 plus. It gives a hydrogen to water and leaves you with that. Notice this time I wrote in the water. I didn't have to. I could have just written it as H plus, but I decided to. And now with how it's written here, actually this is the acid and this is the conjugate base. So it's kind of just a different flip-flop in how we're thinking about it. But because we actually added the NH4 plus, it's an acidic ion. All right, next one. Oh, and this H3O plus right there, that's the thing you look for to know that it's acidic. So if, let's say that first little way that we talked about it as the conjugate acid didn't make a lot of sense to you, and instead you want to think about it in terms of these equations, what you always look for is if it's giving off an H plus or an H3O plus, you know it's acidic. What is it going to give off if it's basic? There's going to be an OH minus there somehow. All right, next one. An NO2 minus. First off, what's the name of it? I like that. It was quiet. So what is it? So is it nitrate or nitrite? It's nitrite. Okay. Now, acidic, basic, or neutral. So we want to think about, is it a conjugate acid or base? Usually with the ions, that's the easiest way to think about it. What do we have that we know that's related to this? Nitrous acid, right? And we can call that the conjugate base of nitrous acid if we wanted. So is it going to be acidic, basic, or neutral? Basic. If you say, I really don't like thinking about it that way, I'd rather think about how it reacts with water, you can do that too. So we can think about how it reacts with water. It's a negative ion, so since it's a negative ion, it's going to pick up a hydrogen. Right? Positive ions would give off the H plus generally. There's exceptions to this, but generally. Okay, so what does it leave off? An H plus or an OH minus? OH minus, so what is it? Basic. One more. Is a chlorine ion acidic, basic, or neutral? What would be the conjugate acid of this? HCl. That's the thing we're used to thinking of. So now the question is this a base? We have to decide, is it going to pick up a hydrogen, right? That's what we decided with the other ones. Is it going to give off a hydrogen? Is it going to pick up a hydrogen? So first off, if this is going to do it, would it pick up or give off a hydrogen? It's got to pick one up, right, because it's a negative ion. So then the question is it going to? Will it do that? What do we know about HCl? It's a strong acid, which means what? It completely dissociates, so completely breaks apart. If it completely breaks apart, is that chlorine going to go pick up a hydrogen? No. It's a strong acid. It completely breaks apart. It's not going to do that. So is that reaction going to happen? No. So is this acidic, basic, or neutral? It's neutral. So that bottom situation comes up whenever you have something where the conjugate, whether that be the conjugate acid or the conjugate base, is a strong acid or base. Okay? Whenever picking up a hydrogen or dropping off a hydrogen would form a strong acid or base, it's not going to react with water. It's not going to do that. And so you get a neutral species. All right? So I didn't ask you this one, but let's do one more, just because it's good to have the other example too. Let's look at sodium plus. So Na plus. If you had Na plus, what species is related to that we're used to thinking of as an acid or a base? NaOH, right? So NaOH is an acid or base? It's a base. So Na, is that going to pick up an OH minus? Would it pick up an OH minus? No, and it's because that sodium hydroxide is a strong base, right? So if ever you're forming something that's a strong acid or a strong base, it's not going to do it, just like this one. So that comes up with all like potassium, your whole first and second group elements, lithium, it's not going to do that. It comes up with all your halogens, your fluorine, chlorine, bromine, iodine, it's not going to do that. So those are your neutral ones. Now I say these are stepping stone examples because I'm not going to ask you this. I'm going to give you a full salt and say, is this salt acidic, basic, or neutral? And then you have to decide it for each ion, okay? And then that will tell you. All right, so we have our three types of salts, acidic, basic, or neutral. Here's how you want to go through and decide what is going to happen. First off, ionize the salt, if possible. We have not yet learned about salts where it's not possible, and so therefore it'll be possible. Once we hit KSP, we can kind of integrate these things in and talk about salts that are less soluble or very close to insoluble. But for right now, they're going to be soluble, so you let them break up in water. You let them ionize in water. Now you kind of have two of the problem that we just did. You have a plus ion, you have a minus ion, and you're going to do what we just did on the last slide for both of them. And here I say react with water. Or in other words, you can put in little brackets or next to that, do what we did on the last slide, where we say, okay, I have my two ions. Is the first ion acidic or basic or neutral? And is the second ion acidic, basic, or neutral? Now, again, this is what we did on the last slide, so it's just putting in words what we did on the last slide. You need to think of two things. Once it reacts with water, what is it going to form? So you can also think this as this of, is this the conjugate acid or base of something that we recognize, right? We react it with water, what is it going to do? Anything that leaves off an H3O plus is an acid. Anything that leaves off an OH minus is a base. Now, if you're pretty comfortable thinking about acids and bases and you've spent a lot of time on the homework or you just have a good background on it, you're welcome to look at this and say, just like we did on the last slide, oh yeah, nitrate, that's the conjugate base of an acid I'm familiar with, HNO2. So I know that that's basic. You can also look at it like that. There's just different ways of saying it. The thing to watch out for though is to remember that if that thing you're used to recognizing, that sodium hydroxide or that potassium hydroxide or that hydrochloric acid, if whatever that is strong, a strong acid or a strong base, its conjugate is very, very, very weak. So weak that it's not going to do it. It's not going to react. And so that's neutral. Okay? So that's just in words what we did on the last slide. And then really the best way to do these is just lots and lots and lots of examples. I think, yeah, we're going to do them on the document camera. Okay, this is the more realistic version of how I would ask it. I would say, all right, is this acidic, basic, or neutral? And I'd give you a full salt. So in this case, the first one is, well, actually salt, sodium chloride. The first step I say is break it up into its ions, right? For the record, what I'm doing here is excruciatingly detailed in the amount of work. I'll show you afterwards how much work I would do for each one, if I were one of you guys taking a test on it, I guess I should say. So first, excruciatingly detailed version. We break it apart, and we form Na plus Cl minus. We look at sodium, and we say, will that or will it won't react with water? So that's a little question mark up there, like, hey, will it? If it were, would it pick up an OH or would it pick up an H? OH. And that's just because it's a plus ion, right? You'd want to neutralize the ion or the charge. And we form this. Is this going to happen? No. Why? That's a strong base. That's not going to happen. Okay. Now let's look at the chlorine. It's a minus ion, so what would it pick up from water if it was going to? Yeah, it's a negative, so it's got to pick up a positive. Is that one going to happen? Nope. Why? Yeah, HCl is a strong acid, so that one's not going to happen either. So is this going to happen? Or, I'm sorry, let me rephrase. Acidic, basic, or neutral? Neutral. Both are neutral, it's neutral. Now, the amount of work for this that you should show on the exam, I'll circle in pink. Purple, because I've already used pink. Yeah, that's it. Don't show me work for something like this. You can think about it, you can write the work out, but this is something you want to kind of be able to walk through in your head and say, okay, I got sodium plus, that's related to NaOH, it's not gonna happen, it's neutral. I got chlorine, that's related to HCl, that's a strong acid too, that's not gonna happen, it's neutral, okay? So this is the written out version of that, but you don't need to show that. Show it for like a week or so until you get the hang of it, and then stop. Next one. We're gonna break this one up into sodium plus. Recognize this little pattern in here, that COO minus. Don't need to know the name of it, but it's acetate. That's the one I like to use as examples. We can look at each one. I'm going to cut down on the work a little bit here because of the sodium we've already done. The sodium is the same as this, right? It hasn't changed. So what is the sodium? Acidic, basic, or neutral? So it's not basic because first off, if it was going to do anything, it would actually be acidic because it leaves off an H+. But it's not going to do that anyways because this is strong. So it's not going to do that. So this one is neutral. If you want to show the work, you can write it. Maybe you just want to draw a little arrow and say we already showed it. I'm going to write out the work for this one though. This line of work is something that you may actually want to continue doing right up to the exam. Some of you may not want to and you don't have to, but I think for a lot of people it's probably a good thing to do. So if this happens, is it going to pick up a hydrogen or is it going to pick up an OH? What's this charge? Minus. So what would it want to do? Pick up a hydrogen. So it leaves off an OH minus. It leaves off an OH minus. So is it acidic, basic, or neutral? Basic. And this is weak, so that'll happen. That's a weak acid. We know that's a weak acid. So that'll happen. We know that that equilibrium is an equilibrium that is set up. So that's why I put the little check mark there. So this one is neutral. This one is basic. What is it overall? Basic. Talking through it a slightly different way. We recognize this, maybe, as the conjugate base of something that we recognize as a weak acid. And so we can see that this is going to be basic, okay? So that's just a slightly different way of thinking about it if you want. It saves you a little bit of work. Okay, now pretty much comes a time where you want to try to start beating me to the problems, if possible. This one, you may need a little help in the split because it's a little difficult to see. But we have that pattern where the nitrogen is bonded to three things or has three bonds. And then we have the chlorine. So you can think of this as just a souped up ammonia, right? Or a souped up ammonium, I guess. So we have this. The chlorine, I'm not going to show the work for it because we did it up here, but if you want, just draw a little arrow down so that you can see that we did the work from here. Chlorine would pick up a hydrogen if it was going to and become HCl. But we recognize HCl as a strong acid, and so that's not going to happen. So the chlorine is just neutral. I'm just going to put a little X through it and write neutral. Now I'll do the work for the other one. Yeah?
What is the 4 and why is it H4?
Because I was talking about doing a souped up ammonium ion when I wrote it, and I turned it into an ammonium ion when I wrote it. The plus still belongs there though. Sorry about that. So ammonium is in H4, so that's what happened there. Okay, so let's go ahead and write this. We're recognizing it as that pattern of, well, with the bases, we talked about nitrogen bonded to 3 things, right? But this is kind of like that, except we have that extra hydrogen there. And it gives off that extra hydrogen. To become neutral. Okay. Is this strong or weak? It's weak. Remember, our bases are kind of our easier one to know are strong versus weak because they're just that first and second group. Hydroxides are our strongs. Everything else are weak. Okay, so that one's all right. We know this will happen. So now, is this acidic, basic, or neutral? So we have neutral and we have acidic, so overall it's going to be okay. Ki. This one I'm going to do exactly the amount of work that I would expect from you on an exam, okay? All right. Ki, it splits into 2 ions. Which ions? What's the positive ion? K plus. And what's the negative ion? I minus. Let's take potassium first. K plus. If that were to pick something up, what would it become? KOH. But what do we know about KOH? It's a strong base. So is that going to happen? So K is neutral. Now I. If we have I, what is that going to pick up if it were to? H. And what do we know about HI? It's a strong acid. And so what do we know about the iodine ion? Is it acidic, basic, or neutral? So both the plus and the minus ion are neutral. What is it going to be? Perfect. You still want to go through the thought process. You can just do it in your head. Yeah?
In the chance that you get one acidic and one basic, would it be neutral?
Not quite. Give me a minute and we'll talk about it. That gets a little bit more complicated. Yeah. You have to actually do some calculations when that comes up. Or at least do some looking at numbers. Okay. KNO3. Same thing. We're going to do the same amount of work that would be required on an exam. Potassium. Let me rephrase. Which 2 ions do we have? K plus and NO3 minus. Okay. What is NO3 minus called? Nitrate. All right. So let's take potassium first. So we have K plus. What would it become? KOH. Now, is that going to happen? No. Why? Because KOH is a strong base, right? So if you're making a strong acid or a base, it's not going to happen. All right. So potassium itself is neutral. Now what about the nitrate? Let's do the work for that one. Again, this you may or may not want to do as time goes on. It's up to you. I think for a lot of people it's still a useful exercise. It's a negative ion, so what is it going to pick up? Is it going to pick up a hydrogen or a hydroxide? If it were going to do it. It would become that, right? Now, what would it leave off? Now, is it going to do it? Why? Yeah, the reason, and you may be saying, well, why did I do the work for this one if it's going to be the same thing? We didn't do that for the other one. This is, some of the polyatomic are, they're less likely for you to necessarily pick up. They're not quite as in your head as the fluorines and the chlorine and the iodine and the bromine. So that's why I wrote out the work. You still wouldn't have to. I just chose to in this case. So it's still neutral. Okay, last one. Potassium. Is that going to be acidic, basic, or neutral? Potassium? Just the potassium, sorry. Just the K plus ion. That one, just the K plus ion would be neutral, right? So I'm trying to show you all the different amounts of work that you may or may not want to do. As for what is right or wrong, only you can answer that. It's up to you. Nitrate. Let's talk through this one the other way. We can write the equation if you want. You may want to go through and do that real fast. But what would the nitrite ion be? What are we used to seeing it as in acid form? Nitrous acid. Is that a weak acid or a strong acid? Weak. So overall, is this going to happen? Is it going to react with water? Yeah. I would write out the work for it. It's up to you on this particular level. It's very person specific. I would probably write it out, right up even until exam time. We have an OH minus. So what is this going to be overall? Basic. Okay. There are, the next slide is just for you at home. So there's a you try example section. Give it a shot at home, look at it. We're not done, we have 8 minutes left, guys. But go ahead and look at it, spend some time on it, and ask me if you have questions. But for the most part, it kind of seems like you guys got this. So the answers are there if you need them. So now let's talk about what happens. And this is under the harder example slides if you want to look at it. Now I'll finally answer the guy's question in the back who said, but what if you have both an acidic and a basic ion? Now some things change. Because now you have to decide which one wins. Okay? You can't just say it's neutral. There's definitely, that's a good first guess. To say, okay, what if I have both an acidic and a basic ion? They'll just cancel each other out. But we know something about acids and bases. We know that they aren't identical in strength, right? Sure, we sometimes group them into strong and weak to simplify things a little bit. But in reality, there's a gradient there. So when you put two of these together, one acidic, one basic, you have to see which one wins. And that's where that last little bit of the section that we just did comes in handy, where we start talking about the strengths of the conjugate acids or bases. So let's do at least one example. We start off the same way as before. And I'm going to go back to writing out the work all the way, since these get a little more complex. Now, based on last time, let's do what we did. So NH4 plus, is that going to be acidic, basic, or neutral? Acidic, right? Let's write out the reaction for it. If you're saying, I don't want to write out the reaction for it, that's fine. It's up to you. I think it's probably a good idea. Because of this one too. So what is our NO2 minus? We've used that in examples a couple of times. Is that acidic, basic, or neutral? It's basic, right? Because it picks up a hydrogen to become HNO2, which is weak. We have that. One case we're giving off an H3O plus, and one case we're giving off an OH minus. Which one gives off more? Now, it's a 1-to-1 ratio just because of the way the salt is. So we know that we have one of these and one of these. That doesn't help us out. We need to see which equilibrium is further to this side. What number do we have that is a measure of equilibrium, just in a generic form? K, right? Because the bigger that K is, the farther the reaction is to what side? The products, right? Higher K equals higher products. So what we want to do is we want to get the K for each of these equations. And notice I'm being pretty vague with my subscripts. I'm just saying K. We want to get the K of the equations, and we want to see, well, which one is bigger? The bigger one wins, okay? What we have to be a little bit careful of is that we grab the right numbers. Because if you go to the back of the book or the internet and you look up a number for this, you're not going to find the Ka for NH4+. What are you actually going to end up finding? You're going to find NH3, and then that's going to be the Kb. So you can't look up that number. And that's where I made I call it a joke, but it really wasn't a joke. It was me warning you about the going to Yahoo Answers, because you'll definitely find this if you just go like randomly searching on the internet. But the thing is, that's not how we tabulate them. That's not how we talk about them, because we'd always have to tabulate 2 values for everything, and that's a waste of time and space. And so we don't do that. We tabulate Kb's for bases, and we tabulate Ka's for acids, and we know as chemists, everybody else can figure out the other one. So if we want K for this, and all we have is Ka for NH3, or excuse me, Kb for NH3, what do we do? What do we use? Kw over Kb. And you can go to the table and you can look up the Kb for NH3 to get your answer. Similarly, you go to look up what do you need here, Ka or Kb? You need Kb, and you go to look up the Kb for for NO2 minus, and you don't find it. What do you find? You find the Ka of this. No big deal. You just do Kw over Ka. And the bigger one wins. So which one here is bigger, the Ka or the Kb? So is it going to be acidic, basic, or neutral? Now, if you are good at looking at numbers and thinking about increasing or decreasing or whatever in your head, do you have to do this math out? You don't have to, because you can look at it and you can say, oh, as the Ka goes up, the Kb goes down. And you can look at this and say, okay, this is my smaller Kb. This is my smaller value here. So that's going to make this one bigger. And that's fine. You're welcome to do that. The problem is that most people have a hard time flipping numbers like that in their head. So at least for the beginning part of this, I would suggest figuring out the number, even though you never actually use it and can do everything with increase or decrease. We'll stop there, but as before, go ahead and try those next 2 problems on your own so that it's a little bit quicker to go through next time and you have some idea of what we're doing, and if you're wrong, we can fix it and things of that sort. So give them a shot before we go on.